Okay, kids. So Uncle Starach is back with another exciting episode of Thermodynamics. Hey, try to contain yourselves, okay? All right. So here's a question that will be similar to what you're going to be seeing on your classwork very soon because we're about halfway done this stuff now. Okay, now this is a question. It says, a piece of ice at negative 15 degrees Celsius was dropped into 500 grams of hot chocolate at 92 degrees Celsius. After all the ice melted, the temperature dropped to 88 degrees Celsius. How many grams of ice were added? Okay, well, the temperature did not go down all that much. So, and hot chocolate, of course, is made from mostly water, like the Swiss Miss ones that you would put in the mug and you boil water. Okay, so that's what we're going to assume. So we're going to assume that the hot chocolate is mostly water. So let me just give you a little picture. I know the pictures tend to help a little bit. So here's my cup of hot chocolate, let's say, drawn very badly. All right. And there's a piece of ice that's going to get dropped in there. Right now, this hot chocolate, here's what we know about it. We know there's 500 grams of it, which would be about the same amount as what's in the water bottles that you all carry around, okay? And we know that it is at a T1 of 92 degrees Celsius, okay? And the ice that's up here, we don't know how many grams of ice there are. So the M value for the ice is our variable. But we do know it's starting at, I know I have ice at negative 15 degrees Celsius. The only thing is, I don't know how many grams of ice there are. Okay. That is a really bad cup, now to look at. Hey, I never claimed to be a good artist, all right? Okay, so the ice gets dropped into the hot chocolate. Now we got to think about what's going to happen with the scenario here. When the ice gets dropped in, the temperature of the ice has to warm up to the melting point temperature of 0. Okay, so we know it's going to change 15 degrees. Then it all needs to melt, and that's where that enthalpy of fusion comes in, the delta H value of 333 joules per gram. Remember, it takes 333 joules to melt 1 gram of ice. When all of that ice melts, it's going to become water at 0, okay? And then, as all that happens, right, so think about, say this is the temperature of the water. You drop the ice in. Okay, the ice temperature warms up, the water temperature comes down. All the ice melts, the water temperature comes down. Then you have cold water mixed with the warmer water of the hot chocolate, and they meet at a final temperature of 88 degrees. So this becomes our final temperature for everything, is 88 degrees Celsius. Okay, so what we have there, kids, is 4 Q values. Q for the heat energy. You have the Q value for the ice coming up in temperature. You have another Q value for all that ice melting. You have another Q value for that ice being cold water now and rising up to a temperature of 88 degrees Celsius. And then you have the Q value for the hot water, which was in the hot chocolate. That energy is dropping. So all of the heat energy supplied by this system is being supplied by the water in the hot chocolate. Okay, so let's just quickly write out our Q values and what they're going to be. So there's going to be a Q value for ice. There's going to be a Q value for the melting of that ice. There's going to be a Q value for cold water. That's what used to be ice. I'll abbreviate that CW, just like I did in the other one. And then there's going to be a Q value for the water in the hot chocolate. Let's call that HW for hot water. But the sum of all of the thermal energy transfer in this system assuming it's completely adiabatic and no heat is getting lost to the outside, which is not the case, but let's just pretend it is, all right? The sum of all the thermal energy transfer in this system is going to equal 0. All right, now let's talk about where temperatures are changing and where they are not changing. There is a temperature changing from the ice. The ice can only warm up till it gets to 0. I've said this before and a lot of my classes fall for it. I say, how long can you heat an ice cube? Some of them would say forever. Well, yeah, but it's not going to be an ice cube anymore. But heating it forever also would be kind of hard, I think. But you understand the point. Okay, so since the ice needs to warm up, that Q value for the ice is going to have a temperature change. So the Q value for the ice is going to be M times delta T times Cp, right? Of course, the delta T value is the T2 minus T1. All right, but at the melting phase, remember that little graph? When a piece of ice melts, it's at 0 degrees Celsius, and it becomes water at 0 degrees Celsius. That's that enthalpy of fusion. So for the Q melt, there isn't a temperature change. It's just the mass times the delta H of fusion, okay? So we have the equation set up something like this so far. All right, now the cold water is going to, so the ice heated up to 0, it then melts, becomes water at 0. That cold water is going to go to 0 all the way up to the final temperature of 88 degrees Celsius. So there's an M delta T Cp for that. And the hot water, of course, is cooling from 92 to 88, so there's an M delta T Cp for that. So let's assume that since the hot chocolate is mostly water, right? The hot chocolate's mostly water, we will assume it to have the same specific heat capacity or Cp value that water does, okay? Now let's plug in the things that we know. Well, we don't know the mass of the ice. All right, but here's the thing with that mass of ice. We don't have 3 variables, we really only have 1, okay? Because this mass, this ice that we don't know, is going to come up 15 degrees and use the ice Cp, which is 2.06 joules per grams degree Celsius, or 2.06 joules per gram Kelvin, meaning it takes 2.06 joules of heat energy to heat up 1 gram of ice by 1 degree Celsius or 1 Kelvin unit. All right, so we know this value and we know this value. All right, here we know the delta H of fusion is always, for water or ice, is always 333. If ice is melting, it's 333 joules per gram. If water is freezing, it's negative 333 joules per gram, meaning it needs to lose 333 joules per every gram. Okay, but when that ice melts, it also becomes cold water. Now it's 0. But the thing is, whatever the mass of the ice is, let's just make it up. Let's say it was 25 grams, okay? If it was 25 grams, it's going to be 25 grams here, 25 grams here, and 25 grams here. All right, but since we don't know what it is, we're just going to call it M across the board because we know that number has to be the same every time. We just don't know what it is yet. Okay, so for the first part, for the first Q, what you are going to have is an M value, which we don't know. All right, and then we're going to have the delta T. Now, the delta T for this particular one is the ice is going to go from negative 15 up to 0 because you can't have ice past 0 under normal circumstances. So that'll be a temperature change of 15 degrees Celsius, and the Cp value is 2.06 joules per gram degree Celsius for ice, okay? And what we'll get is our little Celsius canceled out there, and it's going to end up being joules per gram. Remember what I said, though. If you're following along with me and you're doing okay, all this is, you can keep the units out as long as all of your units are coinciding. Okay, now we get to here. I don't know what the mass is, but I know it's the same mass as here. So I'm just going to call it M, and I'm going to multiply it by the enthalpy of fusion for ice, which is 333 joules per gram. Okay, so now I have a situation kind of like this, all right? Now let's talk about what happens here. So the ice warmed up to 0, it then all melted. Now I have cold water at 0. That cold water is mixing with the hot water and going up to a temperature of 88 degrees Celsius. All right, so I don't know what the mass is, so I'm still going to call it M. However, the delta T is 88 degrees Celsius, and I'm going to use the 4.184 number because it doesn't matter what temperature the water is, that is the heat capacity value. Okay, so I got Q ice plus Q melt plus Q water plus Q cold water. Now I got to get Q hot water. Okay, well, I know everything I need to know about the hot water. I know its mass. I know its temperature change is going to go from 92 to 88, so its temperature change is -4, and the CP value is 4.184. So here's what I'm going to do. Because I'm running out of room, I'm going to leave the units out and just do 500 times -4 times 4.184, and we should all know that this adds up to 0, okay? You might need to kind of zoom in there to see that a little bit, all right? I have the thing as close as I can get, maybe without it. Okay, well, better than nothing, right? Okay, so let's do some math here. So you got 15, right? We got 15 degrees Celsius times a CP value of 2.06. So this is going to become 30.9. And I can call it joules per gram times M if I want. All right. Here, can't really do much. I'm just going to keep it as 333 joules per gram times M. Okay. Plus, well, 88 times 4.184. Hold on. I did times 4,184. Is 368.19. I'm going to call it 368.2 joules per gram times M. All right, and this part here is going to end up being negative because I still have plus, but 500 times -4 is going to end up giving me -2,000, right? So to go -2,000 times 4.184 is going to give me plus -8368. But I think you should all know now that plus negative is just minus, and it'll be 8368, and we'll call it joules, and it's going to add up to 0. Okay, so I don't know what's in the way there as far as the light. Oh, it's probably the phone. All right, anyway. Okay, so we now have the equation set up that we can start to add it up. Now, remember my math scenario about you can't add cats to dogs, right? But you got this much M and this much M and this much M, so all of those can be added up. So we got 368.2 joules per gram times M plus 333 joules per gram times M plus 30.9 joules per gram times M, and that equals 732.1 joules per gram times M. Minus 8,360 equals 0. Well, minus 8,360, if I just add it to both sides, means I'm going to get 8,360 joules here. Now, you guys know, you've been in class with me for 3 marking periods. You know my writing is not that bad. It looks more like the top than the bottom, but I'm having a hard time writing it on the bottom, so bear with me, okay? All right, so now it's just simple math. We're just going to divide by 732.1 joules per gram. Man, that's really bad, by the way. And then 732.1 joules per gram, and joules will cancel. All right, so we got 8,360 joules divided by 732.1 joules per gram, and we get an ice mass of 11.4 grams, or as you guys know, I call them little baby G's. All right? Okay. So you can see a question like this on the classwork, and we'll go from there. I'm going to send you classwork this week. We'll have another live session, as I'm sure you all miss me. Okay? All right. Take care. Be safe, and I'll hopefully see you guys next week.